So this is a review of polynomial functions. So first, you're going to identify the type of function, linear, cubic, etc., graph it, and state the domain and range. So number one is a linear function. It has a slope of 1/3 and a y-intercept at -2. So you draw a point at -2 and go up 1 over 3 in each direction, connect the dots. There's your line. Domain and range are both all real numbers. So for all lines, as long as they're not horizontal or vertical, the domain and range would be all real numbers. Remember, positive slope is rising to the right, negative slope is falling to the right. 1b, this is a quadratic function and it's in vertex form, quadratic. This is telling us to shift left 1. So I'm going to go left 1. And then it has a stretch factor of -2. So the normal parent function for a quadratic has this set of points, over 1 up 1, over 2 up 4, and then if I went further, over 3 up 9, when its vertex is at 0, 0. So this vertex has been shifted left 1. Instead of going over 1 and up 1, I'm going to stretch that times -2 and go upside down. So over 1, down 2. And then instead of 2, 4, I'm going to go over 2 and down 8. So I'm stretching the y value and I'm keeping the x value the same spacing as before. So the domain of quadratic functions is all real numbers, and the range, all the y values are falling below the x-axis, so y has to be less than or equal to 0. Example C is a square root function, and it has been shifted up 2. So I'm going to go up 2. Actually, I'm going to show you the parent function first. So the parent function is 0, 0, because the square root of 0 is 0. The next key point is over 1 and up 1, because the square root of 1 is 1. The next key point, over 4 up 2, because the square root of 4 is 2. Over 9 up 3, because the square root of 9 is 3. So this is the parent function here. So I'm not going to connect those dots. So I'm going to shift each of those dots up 2 units, and then that will be my transformed function. So I am going to connect those dots. So this function starts at 0 because you cannot take the square root of a negative number, and it goes to the right. So my domain is that x has to be greater than or equal to 0. My range, my lowest y value is at 2, and then it continues up forever. So y has to be greater than or equal to 2. Example D. This is an absolute value function, and it has a vertex that has been shifted right 3. So 1, 2, 3 is my vertex. It normally is centered at 0, 0, and it's usually a V-shaped graph with slope of -1 and +1, because the absolute value of any number is the positive of that number. So this time we just have a little bit steeper slope. We've been stretched by 2, so we go up 2 over 1, up 2 over 1 to get our slope of 2 and -2 in either direction. The domain again is all real numbers, but the range is y has to be greater than or equal to 0. Example E. This graph is in standard form. The formula that you need to remember is -b over 2a in order to find the vertex. And so I'm going to take -4 and divide by 2 times 1, because that a value is 1. -4 divided by 2 is -2. To find my y value, I'm going to plug -2 back into the original function. So that would give me +4 here, -8 here, and -3. And 4 minus 11 would give me -7. So I'm at -2, -7 for my vertex. And this is the parent function because the a value is 1. So I just go over 1 up 1, over 2 up 4, and over 3 from the vertex, 1, 2, 3, up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's one other thing that standard form tells you about a function. The c value is the y-intercept. So at the end, we should just double check. -3 was our y-intercept, so we did it correctly. So this was a quadratic function again. Its domain is always all real numbers. This range goes down to -7 and it goes up. Y has to be greater than or equal to -7. If this is going too fast, just pause the video after you watch me complete the problem and then fill in the problem yourself. So it's like doing the problem twice. That'll help you study all the bit more. This is a cubic function, x cubed. So I'm going to show you the parent function for x cubed. 0, 0, 1, 1, because 1 cubed is 1, and 2 cubed is 8. -1 cubed is -1, -2 cubed is -8. So it's kind of this steep curving graph through the origin. It has a domain and range of both all real numbers. My x values can go side to side forever, and my y values can go up and down forever. G is another quadratic that is in standard form. So I have to do -b divided by 2a again. So -4 divided by 2 times 1/2. 2 times 1/2 is 1. -4 divided by 1 will be -4. So now I need to plug -4 into the original function. So I would have 1/2 -4 squared is 16, positive 16. And then I have minus 16, because 4 times -4 is -16, minus 5. Oops, and I'm going to make this go off the graph because this is 8. Minus 16 would be -8. Minus 5 would be -13. So I apologize. Let's just go down 11, 12, 13. Okay, so I'm at -4, -10, 11, 12, 13. We're going to make this come back up onto the graph. This is a shrink. So over 1 up 1/2 is only going to be in between the first two grid lines. Because remember, you're reducing 1, 1, 2, 4, and 3, 9 from the parent function. So you're cutting these y values in half. This will be 1/2, this will be 2, this will be 4.5. So I'm going to go over 2 up 2, so that puts me at -11, and then over 3 up 4.5. So over 1, 2, 3 up 4.5. 1, 2, 3, 4.5. And I just want to show you that y-intercept. When I go over 4, oops, you can't see this, sorry. When I go over 4 from the vertex, I'm going to go up 16. So that would be really going up 8. If I'm at -13 and I go up 8, that will put me at a y-intercept of -5. And that's what the equation told me by the c value that I should be at. So just always use that c value as kind of your double check after you've graphed that you hit that y-intercept. All real numbers for the domain, and the lowest value was -13, so y has to be greater than or equal to -13. H looks like another absolute value function, and it's being flipped over with a slope of -3, and it's at the origin. So at the origin, down 3 over 1, down 3 over 1. So the steepness, this is a straight line, and it has a steepness of 3, and it's been flipped upside down. Domain again is all real numbers. Let's see, all my y values are less than or equal to 0. All right, so what about finding zeros of a polynomial and factoring? So we're going to look for greatest common factor always first. So it looks like I can take out a 3x squared from this term, 3x squared. I would have x squared minus 1 left. then I should check to see if it can go further. This is difference of squares, so it can go further. It would be x plus 1, x minus 1. So my last step is to discover the 3 zeros. So I ask myself, what will make this 0? 0 will. What will make this 0? -1. What will make this 0? +1. Then it says to state the multiplicity of each 0. Remember that when you're graphing, even multiplicity will bounce off the x-axis when you're graphing. Odd multiplicity will cut through the x-axis. So 0 is going to have even multiplicity. 0 is even multiplicity. Negative and 1 are odd multiplicity. And I just want to show you how the graph of this will appear, just so if you have to graph these. So 3x raised to the 4th power minus 3x squared, and I'm just going to hit zoom 6. See if I can get this to focus a little bit more here. All right. So we had said -1 and 1, the graph would cut through, and at 0, the graph would bounce off. So see how that has happened? All right, part B, there's no greatest common factor. This looks like a box method, 3 terms, the A value is bigger than 1. So you start by setting up your box. So you're going to put 2x squared and 4 in the box. And you're going to do a diamond with 2 times 4, so A times C. 8, 9 goes in the bottom of your diamond. What are the factors of 8 that add up to 9? 8 times 1. So 8x and 1x go in your box. And I think that's the hardest part, is just the box. Now filling out the box is easy. This would be 2x times x is 2x squared. 2x times 4 is 8x. 4 times 1 is 4. So my final factors would be x plus 4 times 2x plus 1. Once I have my factors, I need to write down what x would equal. So x would equal -4 or -1/2, because if I set this equal to 0, I would subtract 1 to the other side and divide by 2. And the multiplicity for both of these is odd because they both appear once in the problem, or they have a first power right here. That's not written, but we know that they only exist once. Finally, an easy one. C is just difference of squares. X plus 5, x minus 5 is the pattern. So x is just equal to plus or minus 5. If you'd rather write -5 or +5, that means the same thing. The multiplicity is that they're both odd. Part D looks like greatest common factor. So you always check for greatest common factor first. I would factor out a 2x. I have x plus 10 left. So x can either equal 0 or -10. Again, they only appear once, so they both have a multiplicity that's odd. Looks like I have another difference of squares. So x plus 10, x minus 10. So x is plus or minus 10, and they both have a multiplicity, again, that's odd. They appear once. 1 is an odd number. F, this is already in factored form. So x is either -3 or x is +2. This has an odd multiplicity. This has an even multiplicity. So at 2, the graph will bounce off the x-axis. G, this looks like a box method again. So you could pause the video and try it yourself first, or just watch the video. So 2x squared and 3. The diamond would be 2 times 3 is 6. 7 goes in the bottom. The factors of 6 that I want are 6 times 1. 6x and 1x. These are interchangeable, so you can put them in either place. This looks like 2x times x times 1 times 3. 1 times 3 is 3. You could double check. X plus 3 times 2x plus 1. X is either -3 or -1/2. They both have a multiplicity that's odd. Letter H. Can I factor that? I could factor out a greatest common factor, but that's not going to help me solve this because this actually has no solution. So how did I know that? This is a quadratic that's a sum of two squares. So it's not factorable with our difference of squares formula. And this in standard form, it is just being shifted up 9. So a quadratic that's shifted up 9 and is concave up will never hit the x-axis. So it has no real solutions. And this asked me to find the real zeros. Okay, letter I. Let's see, so 0, -1, +1. This has a multiplicity that's odd because it's to the first power, multiplicity that's odd because it's to the third power, and multiplicity that's even because it's to the fourth power. The last step was kind of putting together a bunch of information and sketching a graph and using a calculator when you needed it. So on number 3, standard form, to find the y-intercept, you plug in 0 for x. So my y-intercept is at 0, -3. State the degree. The degree of this function is 5. That's the highest power in standard form. The maximum number of turning points. So max turning points is 1 less than the degree. So remember, a linear function will never change direction, so it has 0 maximum turning points. A quadratic function has degree 2, so it has 1 turning point for quadratic, right? A cubic function, degree 3, has maximum of 2 turning points. Why do we say maximum? Well, because if you had a cubic function that looked like this, you actually have 0 turning points. It never goes like from increasing to decreasing. This is increasing the whole way. But this cubic function does have 2 turning points. So we say maximum turning points. Maximum real zeros is equal to the degree. So maximum real zeros is equal to 5. And that we say maximum because think of our friend the quadratic. A quadratic, degree 2, could have 2 x-intercepts. But it could also have 1 x-intercept, and it could also have 0 x-intercepts. So we say that it can have a maximum number, but it's not necessarily the number. End behavior. Okay, our end behavior rules. We look for the leading coefficient in standard form. That's negative, so our right end is going to go down. Then we look at our degree, which is odd. So the left side is going to go opposite what the right side is doing, down, so up. If this had been even degree, they both would have gone down. Sketch the graph using a graphing calculator. So if I was going to use the graphing calculator, I would go to the y equals menu, -2x to the 5th plus 2x squared plus x minus 3. And I'm going to go to zoom 6 just to get a 10 by 10 viewing window. And so that's what my graph looks like. It kind of comes down through like 1, has a turning point at kind of right before and after my y-intercepts. So it says, can you locate local maximum and minimum using the calculator? I'll just show you how to do that once. Let's find this point right here. That would be considered a maximum. The graph comes up, changes direction, and has this maximum, but it's a local maximum. The overall maximum is positive infinity. So you go to second trace, which is the calculate key, maximum, which is choice 4. You move your cursor using these arrow keys to the left of that maximum and hit enter. Use the arrow key to go beyond the maximum on the right side and hit enter, and go back to the top and hit enter. So the maximum is at 0.81, comma, -1.58. So 0.81, comma, -1.58. And if you had wanted to locate this turning point, you could just go second, calculate minimum. Do the same thing. All right, Let's do B together, and then you're on to the guided practice on your own. The y-intercept, when I plug in 0, looks like I get 0 because there's no constant. The degree is 3, so that makes the maximum turning points 2, 1 less than the degree. The maximum zeros, it makes 3 because that's equal to the degree. The right end is going to go down again, negative leading coefficient, and the left end is going to go up again because I have an odd degree again. And then let's see what this graph looks like on the graphing calculator. Negative x raised to the third power plus 4x squared plus 3x graph. So if I was just going to sketch this graph, I don't know all these key points. It doesn't say I have to find the x-intercepts. But let's just say I wanted to find this x-intercept, even though the question didn't ask me to. It's not crossing an integer. So I would go to second, calculate 0, choice number 2, hit enter. And then I have to go to the left side of that 0. So I'm moving my cursor. Okay, so now I'm to the left. I'm going to hit enter. I'm going to move my cursor below and hit enter. And then I'm going to go back and take my best guess and hit enter. So this x-intercept is at 4.6 comma 0. So being able to locate x-intercepts is also important. So now you should be working on the guided practice on the back page.